Welcome everyone to this presentation. We are Alejandro Ruiz Fernández de Angulo and Oscar Luque Cabezuelo, students of Architecture Master at the University of Seville. We have developed this work, Analysis and Results, derived from the development of the dynamic metric Partial Daylight Autonomy, or DAP, for seasonal spaces and its application to non-university classrooms, in collaboration with Miguel Ángel Campano and Ignacio Javier Acosta, inside the Research, Development and Innovation National Project DINALIGHT, for efficient design for biodynamic lighting to promote the circadian rhythm in shift work centers, by the investigation group TEP 130 within the University of Seville.
This work proposed a development of the results and a further analysis about the partial daylight autonomy dynamic metric for daylighting, which is based on the daylight autonomy that allows a more accurate natural lighting study for any seasonal use space. In that way, an optimization of window gaps in facades and more efficient lighting levels related to the real necessities of the space could be reached. Thus, all the concepts and previous study about this metric are supported by a mathematical basis and also applied to non-university classrooms.
In the current context, with the 2020 Horizon Insight and global awareness about the importance of optimizing the use of energy, it is necessary to reach an efficient method for designing the size of the windows in order to take advantage of daylight, for which the dynamic daylight metrics can be used. In Spain, around 20% of the electricity consumption is made by buildings, and moreover, the 28% of it is due to the electric lighting, so that making predictive computational models analyzed with dynamic matrix can mean a decrease on the electricity consumption, both due to the window size optimization and the use of smart controls of the architectural spaces. Nevertheless, there is a casuistry that dynamic metrics do not consider, as many buildings have a temporary use throughout the year. For example, educational centers that have no use around the summer period. This type of building is highly widespread throughout Andalusia, where there are more than 7,000 public schools. So saving part of the energy consumed by electric lighting systems of these schools can result in a large-scale energy savings.
However, this association or activities from daylight carry some health problems among humans, increasing the risk of developing some diseases strongly related to the desynchrony of the circadian rhythms. The aim of this work is to develop a deeper research on the potential of a new lighting dynamic metric, the partial daylight autonomy, which has been previously introduced at the ICCAN of 2019. Thus, it will be possible to consider the non-use period of a space and so not oversizing nor the penetration or amount of natural light that comes through its windows, allowing to fit window gap size to the real conditions and necessities of the room. So as to verify the impact of this metric, it has been applied to a case study based on secondary school multipurpose classrooms, defined in a previous article in order to check its behavior considering some concrete guidelines explained in a methodology based on mathematical and comparative analysis of results.
The case study, which has been defined in the previous paper, consists in a conventional secondary school multipurpose classroom of 8 meters wide, 6 meters deep and 3 meters high, having a window gap size of 7 per 1 meters, meaning it the 30% of the vertical plane, oriented north and centered in the facade. The model has been located in Madrid, Spain, with a standard academic year, which means not considering weekends, and an uninterrupted schedule from 8:30 in the morning to 6:30 in the afternoon, and taking into account the DST. All that considering the recommended illuminance of 500 lux. Also, it's been located at 30 per 30 cm calculation grid placed 60 cm above the floor, and the results are obtained from the middle section of the facade.
This program works with the daylight coefficients defined by Joma and has been validated by the international scientific community. The Rhinoceros 5.0 versions have been used to create the 3D model, as it is the interface that supports DIVA. The selected tool for developing the simulators is DIVA 4.0 version, a dynamic lighting calculating software developed by the MIT, based on the radiance calculation engine created by Christoph Reinhardt. The validation process of the calculation tool is one explained in the previous publication by comparison with a real model based on a test that monitors for a full year. For this validation, the calculation database and the experimental results are based on the previous publication of Campano and Company using the mentioned test cell. The cell is located in Seville, Spain, and it's characterized by the dimension of 2.4 meters wide, 3.2 meters deep, and 2.7 meters high, with a windows gap of 1.16 plus 1.08 meters corresponding to the 20% of the vertical plane, centered on a facade and facing south. The 3D model is generated by rhinoceros and subsequently calculating using DIVA, thus obtaining the daylight autonomy values for an uninterrupted schedule from 8 o'clock in the morning to 17 o'clock in the afternoon, including DST, and two different thresholds of illuminance of 100 and 500 lux. Afterwards, a comparison is made between the previous values obtained, both measurements and computer calculated with dicing, and those contained in the present study with DIVA. The maximum divergence among the value is lower than 10% in the worst case, so the validation of the tool is sophistically correct.
To develop this study, several variables have been considered, and so generating the following cases grouped into two sets. The first group refers to physical variables such as window size, which are 30%, 45% and 60% of the surface of the facade, and the reflectance of the materials, categorized as bright for high reflectance materials and dark for low reflectance materials. The second set deals with the variables of the model, such as the window orientation, which are north and south. All variables combined contribute to develop a case study with 12 variables. Lastly, these cases are studied with seasonal occupation schedules, simulating the full standard year without holidays for the calculation of daylight autonomy, and on the other hand, the same year without occupation during July and August for the calculation of the partial daylight autonomy, or DAP, according to the Spanish summer vacation period.
The results obtained of the simulation progress have been analyzed in two different ways. On one hand, a graphic analysis has been carried out studying the pattern of each graphic to group them according to their behavior. On the other hand, a deviation analysis has been made, taking into account the mean and standard deviation of the calculation model with the aim of understanding how each model behaves and what is the numerical impact of the use of DA against the use of DAP. Each casuistry, the ones in the table 6, a total of 8, has been studied with DIVA twice, one considering all year occupation, so obtaining DA, and another taking into account the non-use periods of obtaining DAP. The four behavior graphics group are Group A, where it's possible to find decreasing curves, being DA always is higher than DAP, and they get away from the window, yet never crossing the reaching of the value of 0. All the models with the bright reflectance level can be found in this group. Considering the values of DA and DAP, it has been calculating the deviance of every calculation node. It's worth noting that a shorter interval of days will be a higher divergence between DA and DAP. Furthermore, those specific deviation has been taken in order to develop a proper deviance analysis obtained in a mean deviation and a standard deviation, and has been done with all the results.
In Group B, it can be found graphics which, though following the same behavior as those in Group A, the zero value is reached as getting closer to the room fan. The majority of dark reflectance level models are found in this group. Following the method defined for Group A, they have been obtained the mean and standard deviations for every graphic contained in Group B. In Group C, it is possible to find graphics with a similar beginning to the previous groups, but as they keep warding off the facade, there is a crossing point of the curves so that the DAP gets higher than the DA from that point to the background. A reason for that is associated with the elevation angle of the sun in winter, compared to the one in summer, reaching a deeper penetration level to the background of the room and obtaining so higher illumination levels. A darker reflectance level and south orientation are the main characteristics for these graphics. Besides, due to that values line cross, it's possible to perceive the non-linear correlation between dA and dAp in many of the cases. Following the method defined for the previous groups, they have been obtained the mean and standard deviations for every graphic contained in group C. In group D, they can be found graphics that follow the same pattern as those in group A, although the values divergence is noticed to be decreasing as they get to the room fund, tending to cross. If the depth of the case study room was higher, the behavior of this graphic would be as those in group C, showing the cross of dA and dAp curves. Following the method defined for the previous groups, they have been obtained the mean and standard deviations for every graphic contained in group D.
Considering all the graphics and the divergence, it has been developing a deviation analysis with the mean and the standard deviation specified previously, in order to be able to discretize what variables are a higher impact in the use of not use of DAP. They have been grouped and considering the variables. About the orientation, the deviations are remarkable given that those ones in models facing north are higher, so it is possible to qualify the better efficiency of DAP for north orientation rather than south ones. Regarding material reflectance, variables deviation are found in the same range of divergence, so that it is possible to affirm that DAP would mean an improvement whether the materials of the space have a high or low reflectance. About the size of the window, the deviations are similar and so efficient independent of it. Yet it can be appreciated a light higher deviation for models with 20% window size rather than those with a 45% or 60%.
According to the results and deviation analysis, the use of this new dynamic metric partial daylight autonomy or DAP means a better fit in the results of daylighting calculations for spaces characterized by seasonal use. In accordance with the previous statement, the usually lower value of the DAP metric means that a building with a seasonal use requires a higher energy consumption than the estimated in electric lighting during the period of operation, in comparison with a continuous use building, due to the fact that the summer daylighting is considered into the calculation. Quantifying the previous deduction, the autonomy of daylight can fall up to 24% depending on the orientation, window size, and the study point. Furthermore, according to the previous analysis, it can be noticed that a higher level of exposure to diffuse radiation on the model means a higher divergence between dA and dAp indicators, so that north-oriented models are the best example for the use of the DAP metric. On the other hand, reflectance and window size do not play such a big role in this decision, yet its use is still an improvement in the results and more faithful to the real necessities. Besides, the nonlinear correlation between dA and dAp metrics has been demonstrated, meaning a huge importance of the use of this new dynamic metric that cannot be defined directly from the dA. To sum up, this research demonstrates the great importance of considering the non-use periods of a space in order to develop its lighting study, so that it becomes highly recommended the use of this new partial daylight autonomy metric. Thank you everybody for watching our presentation, and we hope it was useful and instructive.